Melde's experiment is a classic physics demonstration that explores the relationship between standing waves and mechanical vibrations, particularly in strings. It was first performed by Franz Melde in 19th century to study the wave phenomenon. The aim of the experiment is to determine the frequency of transverse mode of vibration and longitudinal mode of vibration, and hence to determine the frequency of the AC main. So the apparatus required for the experiment is Melde's electrical vibrator. A string is fixed at the one end and attached to a vibrating source at the other end, and a long stretch string and a meter scale and a scale pen and some slotted weights of different mass.
Here, now we are going to discuss about the Melde experiment theoretical part. So as we are moving to the introduction part, here Mel's experiment demonstrates the formation of a stationary wave on a stretched string. Also, it is useful to determine the frequency of a transverse vibration of a string under tension. As we can see here, a string is made under tension by an electric vibrator, or we can say a mechanical vibrator or a tuning fork. So it is made influenced here, and in the strings waves are formed. That is, stationary waves are formed here. How are the stationary waves formed? When identical waves are being traveled in the opposite direction, and when it is being superimposed, stationary waves are formed. When the driving frequency matches the certain resonance conditions, stationary waves are formed here. So when is the stationary waves formed? When the resonance condition is achieved, right? So the resonance condition is achieved when the frequency of the electric vibrator and frequency of the string are matching each other. The resonance condition is formed. So this is the basic principle of Mel's experiment. So here we can say that the string can vibrate in different modes. So the modes of vibration are the next topic we are going to discuss here. So modes are different types, that are fundamental nodes, second harmonic, and also higher harmonics are there. So in fundamental nodes, one antinode and two nodes are formed. So here the antinodes are formed at the middle, and also the nodes are formed at the end of the string. Also, points with the node displacement are nodes, and points with maximum amplitudes are antinodes. Also, for higher harmonic, the number of nodes and antinodes increases as the wavelength increases. Also, the distance between any two consecutive nodes is lambda by 2. We'll be moving on to the next slides, and we'll be discussing this through a diagram. Here, as we can see in the diagram, for the fundamental node, one antinode in the middle and two nodes at the ends are formed here. For the second harmonic, two antinodes are formed in the middle and three nodes are formed at the ends. Coming to the higher harmonics, nodes and antinodes increases and wavelength also changes accordingly. For the length of the string, that is, it depends on the wavelength, or wavelength depends on the number of segments formed here. So L equal to n lambda by 2. So here first for the fundamental node, L is given by 1 by 2 lambda. Coming to the second harmonics, L is given by lambda 2. Coming to the third harmonics, L is given by 3 by 2 lambda 3. So it goes on accordingly. So here now we are going to arrive at the general equation for finding the frequency of a vibration. So as we already know, for a string vibration with a frequency f, length of the string L is given by n lambda divided by 2, where lambda is the wavelength and n is an integer. So frequency formula, as we already know, nu equal to f lambda. So from here f is given by nu by lambda. So from this length of the string equation, we already know lambda is given by 2 divided by ni. So here we are substituting lambda as n divided by 2l. So we are getting equation as f equal to nu by L, that is nv by 2l. And we know nu is the speed of the wave in the string, and lambda is given by wavelength. So speed of the wave in the string is given by root of tau by nu. So tau is the tension of the string and nu is the mass per unit length. So this is the equation that we are combining here, that is nv by 2l, and we will be arriving at a general equation for finding the frequency of the vibration in this experiment. The next slide. So here we can see that the frequency of vibration can be, in the general case, is given by f equal to n by 2l root of tau by nu. So frequency is given in terms of tension and mass density. So this is the formula we are using in this experiment. So as we have already know the transverse and the longitudinal mode. So in the transverse mode, the vibration occurs perpendicular to the length of the string. Also the frequency of the string and frequency of the tuning fork is equal. Coming to the equation for the transverse mode, frequency of transverse mode is given by F equal to 1 by 2L root of tau by nu. So this is the equation we will be using in this experiment. Coming to the longitudinal mode, the vibration occurs parallel to the length of the string and the longitudinal mode is occur. But the frequency of the string is half the frequency of the tuning fork because the tuning fork will be completed one cycle and the string's vibration is half completed. That is the reason why the frequency of the string is half the frequency of the tuning fork. Here, frequency of the longitudinal mode is given by F equal to 1 by L root of tau by nu. So we'll be using the frequency of the transverse mode to find the equation and to find the result of this experiment. That is F equal to 1 by 2L root of tau by nu. So this is all about the theoretical part of Mel's experiment. Thank you.
Procedure. In the Melde's experiment setup, a pair of magnet is fixed and an electrical vibrator is placed between them. This vibrator is connected to an AC power supply which makes the string vibrate when current flows. Measure the string mass and length. Calculate the mass per unit volume, that is mu, which is mu is equal to m by L. Fix one end of the string to the electrical vibrator, pass the other end over the pulley and attach the scale pan. Make sure the string is horizontal and the pulley is friction minimizing. Align the vibrator so its motion is perpendicular to the string for transverse wave. Switch on the electrical vibrator. The vibrator will drive the string at a fixed frequency F. Add a small known mass to the pan so that the string is taut but not overly tight. This gives the starting tension T. Mass of pan should be recorded. Slowly adjust the position of the pulley until a clear standing wave pattern, that is, nodes and antinodes, appears on the string. When a clear pattern appears, mark position of nodes. Measure the distance between two successive nodes, that is, lambda by 2. Increase the hanging mass by 10 gram each. For each new total mass, allow vibrations to settle and repeat the measurements. Now, turn the electrical vibrator by 90 degree so that it drives the string along its length for longitudinal waves. Repeat the above procedure and record the measurement for each case.
After studying about the procedure of Mel's experiment, let us now look into the calculation of Mel's experiment. Coming on to the observation, let us recall the formula mu is equal to m by L, where mu is linear mass density or mass per unit length of the string, m is mass of the string, and L is length of the string. And from the experiment, we have noted the mass of the string to be equal to 0.170 grams and length of the string to be equal to 233.5 centimeter. Therefore, mu is equal to 0.170 grams divided by 233.5 centimeter, which is equal to 0.000728051 grams per centimeter, which is also equal to 0.0000728051 kg per meter. And from earlier measurements, we have mass of the pan mp to be equal to 1.1 grams and acceleration due to gravity g is equal to 9.8 meter per second square. With this data, let us go to the tabular column. This is the tabular column for transfer waves. Here is the recorded values from the experiment. The first column is recorded mass mr in grams and the second column recorded mass plus mass of the pan, which is equal to 1.1 grams as we discussed in the earlier slides, that is mr plus mp is equal to mass in grams. In third column we have mass in kg, that is converting the second column mass in grams to mass in kg. The next is tension, that is N is equal to mass in kg multiplied by acceleration due to gravity, that is 9.8 meter per second square. Let's see the calculation for first reading. We got 0.01078 by multiplying mass in kg, that is 0.0011 into 9.8. And the second reading 0.10878, we got it by multiplying 0.0111 into 9.8. It is subsequently same for all remaining readings. And the next column is length between nodes, which we measure experimentally. That is, in the first column we have taken in centimeter and we have converted to meters in the second column of lengths between nodes. Next is frequency, which is calculated by a formula for transfer waves, that is F is equal to 1 by 2L to the root of T by mu. Let's put the values and get the result. 1 divided by 2 into L, we know the value of L from the tabular column, that is equal to 0.19 root of T is equal to 0.01078 divided by mu, that is 0.000072851. So 1 divided by 2 into 0.19 will be equal to 2.63157 to the root of 148.066550. 2.63157 and root of 148.066550 is equal to 12.16825. So multiplying this, we get 32.0216 Hertz. We have recorded this value in here. Using the same formula, we will get the values for all the remaining reading. And the last column L square, we get it by squaring the length between nodes, which is in meter. That is, squaring this meter into meter square, we'll get the values of this. Going on to the second part, that is tabular column for longitudinal waves. The first four columns will be same, that is mass and tension will remain same. And the next is length between nodes. We record the length between nodes for longitudinal waves. So we have 58 centimeter, and which we have converted to meter, that is 0.58 meters. To calculate the frequency here, we have the formula F is equal to 1 by L to root of T by mu. Let's put the values by help of tabular column. 1 by L, the value of L here is 0.58 to the root of tension T is equal to 0.10878 divided by mu, that is 0.0000728. So 1 by 0.58 will be equal to 1.7241. Root of 0.10878 divided by 0.00007280 will be equal to 1494.1260. 1.7241 root of 1494.1260 will be equal to 38.65392. Multiplying this, we will get 66.4053 hertz. We have recorded the value of the frequency here. Using the same formula, we will calculate the remaining all readings. And the last column, L square, is same as before, that is, we will square length between nodes, which is in meters, and we'll square it, that is m square. Squaring all the values of m, we'll get m square. So this is how we measure the frequency for transfer waves and longitudinal waves.
We have seen how to calculate frequency in the tabular column. Now we will calculate the frequency using graph. That is, frequency for the transfer waves. We have given the equation that 1 f equal to 1 by 2l into root over t by mu. If we are further simplifying this equation, we will get f square equal to 1 by 4 into mu into 1 by slope. That's graph for L square versus T, that is x as tension and y as length square. Using the points from the tabular column, we will plot the graph and we will get straight line. For that straight line, we have to find slope. That slope we got 0.76530 meters. If we are substituting the value in the simplified equation, we will get the frequency as 66.9841 Hz. Similarly, we will calculate the frequency for longitudinal wave, that is f equal to 1 by L into root over t by mu. If we are further simplifying this equation, we will get f square equal to 1 by 4 into 1 by slope. Here the graph for L square versus T. As we have seen for transfer wave also, x-axis as tension and y-axis as length square. Plotting the points in the graph, we need to draw a straight line. For that straight line, we need to find the slope. Substituting the values of slope and mu in the equation,
simplified, we will get frequency as f equal to 138.67811156 Hz. The result of the experiment. The frequency of the AC main is found to be in the transverse mode of vibration of the string is from table we will get 65.5294 Hz, and from the graph we got 66.9841 Hz. For longitudinal mode of vibration of the string, from tabular column we will got 90.5176 Hz, and from the graph we got 138.67811156 Hz. The factors affecting the experiment. Tension in the string. Increasing the tension increases the frequency of vibration. We have the formula for frequency. Here we will get higher the tension will give string vibrates faster. Length of the vibrating segment. The frequency is inversely proportional to the length of the vibrating string. So we will get longer the string will give lower frequency. Shorter the string will give the higher the frequency. Mass per unit length, that is mu equal to m by L. A thick string vibrates slower and a lighter string vibrates faster. Mode of the vibration. We have studied fundamental and second and third harmonic modes, that is higher the mode will give higher frequency. Amplitude of vibration. Affected by the resonance condition, at exact resonance amplitude is maximum. Away from resonance amplitude is small. Medium of resistance. Damping reduces the amplitude. In highly damped conditions, the sharpness of resonance decreases. Thank you for watching.